All right, good afternoon, everybody. It's going to take a couple minutes for all the attendees to come in to the Zoom webinar. So just be patient for a minute or so. And when the numbers seem to be leveling off, then we'll do a quick intro. All right. So you'll notice that this is not set up like a normal exit certified class. If you've been to one of our AWS classes before, normally if we do them over Zoom, we like it to be like a regular class where everybody has their cameras on and two-way audio, video. But to open up these webinars to as many people as possible, we run them what we call webinar style. So you can't really turn on your video or ask questions through the mic, but you do have access to the chat. So you're welcome to put chats in there. Let me get it started. Hello from Toronto. Maybe say where you're coming from in the chat so people get an idea of where people are. If you do it to everyone, then everybody will see your chat. That gives you a chance to find the chat so that if you want to ask questions later, you can do so. All right, I think the number of attendees is starting to level off. Good afternoon. Well, it's afternoon in the Eastern time zone. And let's see, we got people from all over. Texas. Oh, Chris, you're in Maine. Oh, we got another Toronto, some Ottawa, Washington State. All right, so we got some morning people. I don't know how much international we have. So far, none. Okay. This is AWS Discovery Days are these short free webinars that AWS has built and authorized training partners like ExitCertified are able to deliver. The title for this one is called Machine Learning Basics. This is the last of 5 of these discovery days. Now we've recorded the other ones, so at the end of the session, I'll show you some resources and where to find the other ones. Today's session is being recorded, but your chat isn't, so you can ask questions in the chat. That won't appear in the recording. You will get an email with a link to the recording, probably in a day or two, something like that. But you won't get the slides. We're not allowed to share the slides, so we're not going to do that. My name is Miles Brown. I'm the Cloud and DevOps Advisor at ExitCertified. If you're not familiar with ExitCertified, we've been an authorized training partner of AWS since 2014, but we've been in IT training since 2001. We do all kinds of training, generally where there are vendors with large training programs, we try to partner with them and offer that authorized training. So when you take a 3-day architecting on AWS class from us, it's developed by Amazon, their lab environments, they certify our instructors. So Chris and myself have both been AWS instructors since, I think, 2014 as well, right, Chris? I think you've been something like that. But Chris Littlefield is going to be your instructor for today because he's the machine learning expert. I do a lot of AWS classes, but not the machine learning stuff. That's his deal. Chris has been working in the cloud for 12 years, something like that, maybe more. I think you started down with a company in Australia, right? Doing e-commerce stuff, and then gradually moved more and more on the data side, and certainly teaches a lot of great classes for ExitCertified in the data analytics and machine learning realm. And so at the end of the session, I'm going to come back and talk about a promo. So if you are thinking about taking any classes from ExitCertified, we'll talk a little bit about some of the good classes that you would take after this. If you're going down that road of trying to learn machine learning, and especially the AWS tool set around it, but maybe even just some Python for data science, there's all kinds of classes that might apply here. And I'll give you a promo code that you can use to get, I think it's $100 per day off. So if it's a 3-day class, a 4-day class, it's $300 or $400 off the retail price. But I can maybe answer some questions in the chat, but I think Chris has probably got the whole thing handled. So I'll let him take it over. Chris, take it away.
Thanks, Miles. Welcome, everybody. I'm Chris Littlefield. I think Miles did a pretty good intro on me. Started in 2010 with AWS as far as a customer and 2014 as a trainer. Got all certifications and teach all the classes, but primarily the more advanced classes. I don't know about being the expert, but I do know a little bit about, quite a bit about machine learning. But probably couldn't see me blushing through the beard when Miles was saying all the kind words. And I am based in Maine, which is about 2 hours north of Boston, if people aren't that familiar with it. This is actually the first module of a 4-day class that Miles is going to walk you through, called the Machine Learning Pipeline on AWS. And that's a really good starting point if you don't have a lot of machine learning background. And so this is basically very similar, not exactly the same, but very similar to the first module of that class. And we want to just kind of level set. So we don't want to bury you in information. But the first link that I wanted to pop into chat was basically sort of the foundational website for AWS and machine learning, just so that you get sort of a handle on, lots of different options. And believe it or not, it's just aws.amazon.com/machine learning. So that's going to have coverage of a lot of different services, not just SageMaker, and you'll find that under the AI services on that page. But the whole idea here is just to give you a taste of what's involved in machine learning on AWS, and then give you the opportunity, hopefully, to join us for a class or two that dives a lot more deeply into the topics and the ML services and AI services within AWS. And obviously gives you that hands-on with labs and sort of real-world use cases. So again, just a brief sort of high-level overview. And as Miles said, you can't ask questions via voice, but if you want to put them in the chat, feel free to. Sometimes I get questions that, would take me hours to answer. So I don't know, I might give you an email address for those kind of questions. But want to just keep it pretty high level. And then if you have questions on deeper knowledge, I might be able to give you links during the webinar. And if not, you can always email me questions sort of as you're going through the journey. So I'll put my email in chat now, in case I forget to do so later. So again, we're going to kind of start slowly. We're going to talk about a kind of overall business need and kind of one of the traps of machine learning. There's an expression, I think, in law enforcement that if you have a hammer, everything's a nail, sort of implying that, when you're in law enforcement, you sort of can lead to thinking that everyone is guilty of something, which is mathematically impossible. And so the same thing can be true with machine learning. You're fresh out of machine learning training. The boss comes to you with a problem and you're like, that's going to be solved by SageMaker. That's going to be solved by an AI service in AWS. And what we want to do is kind of slow you down and make you think sort of pragmatically and say, is this something that I could solve by using what we call classical programming or using a programming language and an application? Or is this something where I really do need a prediction, where I need an algorithm to sort of glean something from the information and give me an outcome? And so the first part we talk about is actually the business need. All right, so we just have a sample business need. All right, and this could be fraud detection. This could be whether customers are going to leave or what we call churn. There's so many different machine learning use cases, but in this case, we're talking about product recommendations. And we're going to use past data to make predictions about this. All right, but I'm jumping a little bit further ahead because you might be able to use classic programming to create recommendations if it's a rule-based type solution. So for the next few slides, I want you to think about our business need, which is basically providing product recommendations based on past purchases by a given customer. Now, that's the problem. And in some cases, you could use what we call classical programming. The downside of classical programming is that we need experts in the field of retail, obviously in this case, to say, well, let's set up some rules. So if we have these business rules and this business logic that's provided by experts, we're going to be able to recommend additional purchases that would be of interest to this particular customer. So if they bought helicopters or the quadcopter toys in the past, maybe we can make a recommendation based on, the types of aircraft they're flying. Do they want a drone or maybe a remote controlled airplane, et cetera, et cetera. But the problem here is that with classic programming, and any of you that are programmers are going to be aware, the biggest challenge is oftentimes the human aspect of it, with bias and errors and incorrect information and God forbid, changing requirements as you're building the application. That can be very, very painful and disruptive to the project. So your actual business user might not know how to solve the particular problem. They definitely would not know the programming languages that you would know or your programmers know. So there is sort of a built-in disconnect and challenge of getting information from the customer and building an application to solve that. Basically, kind of preaching to the converted. If you've gone through software projects, you know that it's very, very cumbersome. We can get bad information from the customer. The other thing that we found is that the customer interest can be extremely unpredictable. So maybe someone bought 5 quadcopters, but the next thing that they want to buy is a Pokemon card set or something completely out of the realm of what we've been looking at for recommendations. And the other problem with classic programming is that every rule adds more time to the process. So we could feed purchase history and apply rules for this purchase history to give recommendations. But, in this particular case, classic programming is not going to be our solution. We want to use machine learning, obviously, because of the topic of the discovery day, the whole session that we're doing here. But please, as you're going through, keep an open mind. So although we're talking about a lot of negativity here with classic programming, as far as the outcomes, if classic programming can solve the problem, that may be less expensive and less time consuming than building a platform or building on top of a platform like SageMaker and implementing one or more machine learning algorithms to solve for recommendations. So the main takeaway here is, yes, classic programming is out there, and I want you to keep it as sort of one of the tools that could solve the problem. If we don't need true predictions, if we don't need true machine learning algorithms, and you think you can solve it with classic programming, for example, just looking up products in a database, you don't need a machine learning algorithm to do that. But if you're trying to make predictions on no data or on existing data, then machine learning is definitely what we want to look at. So we're going to kind of compare this classic programming approach with machine learning. But I want you to keep in mind, just be open-minded to a classic programming approach if that works. So as you get a use case, some of those use cases, it might be a small percentage, but some of those use cases will still require or still be better solved with a classic programming approach, writing an application. But obviously for this webinar, we basically want you to think about machine learning. So here we introduce the concept of a model. And a model basically is a trained or packaged algorithm that's going to be applied to our data. So we're going to do the same thing as you can see in classic programming approach, where we take that purchase history and we feed that in with some rules. But with machine learning, we've passed the purchase history and in addition, the site-wide customer and sales data to our model. And then take that model and glean from that input data the most recent purchases. And based on those most recent purchases, the algorithm is going to make a recommendation. So we're going to kind of walk you through that in a very simplified algorithm coming up shortly. But the output of this process is a recommendation based on data that we already have. So that, by definition, is a supervised learning problem, which we'll also cover shortly. So if we look at machine learning, in machine learning, the model or our platform like SageMaker with the model running in it is going to take the data and derive the rules from the data itself. Also, if we have a good algorithm and a robust algorithm, it can adapt to the complexities in the customer data, customer profiles. And if the model is trained ahead of time, we can save time towards making predictions. So later on, when we get into the pipeline, a classic pipeline would have pre-processing and visualization and huge numbers of hours, and a big percentage of your ML projects get bogged down at that stage. So if the project you're on says, hey, we're going to use pre-trained models, that's going to save you a lot of time. But you may need to be ready to train models. And we'll talk about that in a little bit more detail. But if you can get away with pre-trained, or if you have pre-trained models in the organization, that's going to save you a whole lot of time. And that's sort of the trend is when you hear of things like ML operations and pipelines and deploying things in automated fashion. A lot of times pre-trained models are used, or the training is automated using those ML ops processes. So again, if we look at classic programming, that's an option. Machine learning is quite a better option. But we want to kind of take you through, sorry, I went too fast there. We want to just kind of step back and say, okay, well, what's the model? The model is a trained algorithm that is going to be looking for patterns in our data and does not require explicit manually set rules. All right, so again, we're taking that purchase history and site-wide customer data and using the model to basically look at the most recent purchase, and based on the most recent purchase or purchases, make a recommendation using an algorithm. So when you hear a model, that's just a trained algorithm or various, I probably shouldn't get into algorithms in terms of the breadth of them, but there are a bunch of built-in algorithms. So I might put a link in chat just so you are aware of that. And this is going to link to the developer guide for SageMaker. That's a lot of reading for you, but definitely a good resource. But just to give you an idea, these are the SageMaker built-in algorithms, and they also talk a little bit about pre-trained models. So I'm going to put that in the chat for you. And very, very deep level of knowledge there. But they've sort of broken it up on different sort of data inputs, et cetera. And whether you're using SageMaker or SageMaker Studio, those built-in algorithms apply. But again, I want to keep it pretty high level and just kind of talk about a simple algorithm. And in this case, the simple algorithm, remember our challenge here is to create a recommendation. So they want to talk about features and weights to kind of get you started. And I'm going to kind of build in a little bit extra to the definition there. So you see the equation on top. We're going to sort of fill that in relation to the recommendation algorithm. But there's something I'd like to add to this slide, right? So a lot of people say, what is a feature? A feature is a column, technically, in data, all right? So it might be age, it might be address, it might be zip code, et cetera, postal code. But I like to add to this slide, a feature is an important data point as it relates to predictive outcome. So an important data point as it relates to predictive outcome. If the feature doesn't have any relation to the predictive outcome, it doesn't matter, and we want to get rid of it. All right. So a feature is an important data point as it relates to the predictive outcome. So if zip code doesn't make any difference to the prediction, we want to get rid of it. That means removing an entire column of data. The feature basically is any data that we use to come up with a prediction, and technically what the algorithm or model is going to use to come up with an outcome. And an outcome is called a label. We don't really talk about it at this point, but label data means that we have data where we know the outcome. So the recommendation, for example, would say, well, we already know that we're going to recommend a hat, or we're going to recommend a hat from a brand Y or a particular brand. But in this particular case, if you follow along, you can see that that first X value is the product hat. That is going to equal 1. All right. So a feature is an important data point as it relates to predictive outcome. And you might, it depends on the data set. So I've worked with auto companies, and they have millions and millions of features. If you look at large learning models, we've got, they're looking at things like billions and billions of features and values and so forth. So there can be lots and lots of features, but we basically want to make sure that the features that we're using relate to the predictive outcome. If they don't relate to the predictive outcome, we want to get rid of them. It's basically called dimensionality reduction. And there are also algorithms that can solve from that. There's at least one of the built-in algorithms called PCA will solve for that. So let me get it simplified here. So we have features and weights. A feature is an important data point as it relates to the predictive outcome. And then the weight basically says, how much does this particular feature affect the accuracy of the prediction? So in this case, the customer's purchased 8 hats in the past. So the A variable that we're looking at up top is 0.8, and the X value is 1. All right, so we're going to basically plug that in. And for that first one, we're going to do 0.8 for the weight. And then the 1 is our feature for the X value. So is it brand Y? Yes. So value is 1. If it was no, it would be 0. So keep that simple. And then 2/8 of the items this person bought in the past was from brand Y. So our weight ends up being 0.25. All right, so we're going to plug that into the next value and basically say, okay, well, 0.8 times 1 plus 0.25 times 1 equals a value of 1.05. And we basically set up a rule that we're going to recommend this product if the outcome is 1 or higher. So in this particular case, we're going to recommend that this customer check out this hat from brand Y. We're going to recommend this product to this particular customer. So the most important thing to remember is we're talking about features and weights. And so the feature, remember, is an important data point as it relates to the predictive outcome. And then the weight is how much that feature affects the accuracy of a prediction. And the thing to kind of stop here on is most of the students that I have in classes are panicking about math. They're saying, I'm not a math guru. Very few people actually write these algorithms. All right. A lot of these algorithms are pre-built, pre-provided by Amazon. You might have other folks in your organization that create algorithms, but the math for the most part is done by the platform like SageMaker. And a lot of times, if you know AWS, you'll see that it's emitted to a service called CloudWatch. So there are a lot of heavy duty math, and math will help you if you're into it. But a lot of that work is done by the actual platforms at AWS. So it's not that scary to get started. A lot of the results are emitted inside the platform and also to external services like CloudWatch, for example. So let me know if you have any questions in the chat. We're basically going to kind of switch gears and talk more high level about machine learning. And we do have sort of a comparison later on. Like you may have heard artificial intelligence all over the place. We're going to kind of explain to you where it all fits in. So AI, then ML is a subset of AI, and then deep learning is a subset of machine learning. But we're going to give you an example using chess a little bit later on in the slide deck. So that was features and weights and just a simple algorithm, or very simplified algorithm to kind of explain how that's calculated, but that's all done within the platform. That's done for you. But what we want to talk about next is the sort of categories of machine learning algorithms. And we're going to keep it sort of high level and talk about supervised, unsupervised, and reinforcement. Give you some examples of each of those. And then we'll go and talk a little bit more in depth about deep learning. And then after that, we'll kind of take you through the machine learning pipeline as it relates to an Amazon use case. So let's start off by talking about supervised learning. With supervised learning, you're basically talking about a situation where you have training data where you know the outcome, i.e., you know the data, the data labels. All right. So for that hat example that we looked at in recommendations, we might already have that purchase history we showed you, and we already know the outcome of past purchases, and we're going to use that to predict future purchases with recommendations. In the case of fraud, we might know with the data set in our training data, whether it was fraud or not fraud. In that case, we want to use supervised learning. Unsupervised learning is more apt or more suitable when we don't know about the outcomes. We don't have labeled data. And then reinforcement learning is quite a different genre, so to speak, within machine learning, where the devices or robots or self-driving vehicles learn from their environment, learn from their experiences. So in supervised learning, you're typically the supervisor. So they give you an example here of a VW Beetle and Mazda SUV, a Ford Mustang, and all this data has already been labeled by people. So we've already spent the money or the time or both getting this data labeled so that hopefully when we pass this black Mercedes in, that it's going to pick up that it's a black Mercedes and not focus on the farm or the little fence for the horses or any of the other stuff that's on that particular picture. We want it to focus in on the car, and from the past label data, predict that that's a black Mercedes. All right, and when you go through this process, it's very iterative. And you may find that it catches the barn or it catches the trees in the background or the fog or something else. We want to basically make sure it targets the automobile in the picture and then can label it correctly. And because we're talking about a supervised learning algorithm or model, the data or the outcome is a little bit more likely to be correct because we have past examples. Now, here we're showing you examples where it's not a Mercedes. So if it's never seen a Mercedes before, it's very unlikely that it's going to guess Mercedes from the labeled data. But if it has seen all the different Mercedes that are out there, it might even be able to pick the exact model of this particular black Mercedes. So with supervised learning, we already have labeled data. We already know the outcome. We already know what we're going to predict. But overall, there are 3 different categories for the algorithm to fit within. All right. So the thing to remember with supervised learning is, or to think about, is what are the outcomes that we're looking for? So binary classification, there are only 2 outcomes, ergo the name binary. So it's fraud or not fraud, spam or not spam. Is the customer going to leave us or stay with us? Is the employee going to quit or be retained, et cetera, et cetera? That's just 2 outcomes. That's binary classification. So fraud and not fraud would be a good example for an algorithm built on binary classification. So just replying to a quick chat there. And so basically what we're saying here is, as supervised learning, first thing was we have labeled data, so we know the outcome within our training data set. If we don't have labeled data, we might use a labeling service like SageMaker Ground Truth and use human labelers. If we don't have labeled data and we don't want to pay for a service to get that data labeled, then we would switch to unsupervised, which we're going to cover next. But here we have the 3 categories of supervised learning. So binary classification, if there are only 2 outcomes, then binary classification is the right type of algorithm. All right. So you can look through that in the built-in algorithms, but XGBoost would be an example of a solution or an algorithm that we could use that's built in to SageMaker and AWS, and it will solve, excuse me, for fraud or not fraud in, basically two outcomes. What if we have more than 2 outcomes? That's where multi-class classification comes in. So their example is IT support, returns, accounting, but it can be anything where it's more than 2. So 3 or more outcomes needing to be predicted we would use multi-class classification. And sometimes we're going to use the same algorithm. So algorithms can support 2 of these and sometimes all 3 of these. And we get into the specific algorithms in the 4-day class when we have a bit more time together. But binary classification, 2 outcomes, multi-class classification, 3 or more outcomes. And then regression is quite different. Regression is only 1 outcome and it's a number. So if we were trying to predict the cost of a house based on comparable houses in the area, or if we're trying to figure out how much rent we want to charge in a given location based on the other rentals in the area. In this case, we're saying, okay, well, the share price is going to start at $113, but we're going to predict it's going to go up to $127. All right. So for those of you that are into stock trading, that can be very interesting to say, okay, well, we're going to use machine learning to predict, what's going to happen with the stock. And then we're going to buy the stock based on it going up, sell the stock going down, or might even get more complex and buy options, things like that. But really, if we're supervised learning, these are kind of the three categories of the algorithms that are out there. So binary classification is two outcomes possible, yes or no, or fraud or not fraud examples. MultiClass classification, they talk about IT support, returns, and accounting, but there could be 10 different classes or 50 different classes. Multi-class is 3 or more. And then regression problems are always basically the outcome of a regression problem is a value or an integer, a number. So like a price for a house, how much rent you should charge, etc. So again, all three of these categories have different algorithms, and sometimes the same algorithm can be used for all three of these categories. But a lot of times, we have to differentiate and tell SageMaker, for example, that we want to use binary classification versus multi-class or regression when we talk about the classifier type that can be set before we run the algorithm or run the model. Now, again, all of these relate to labeled data where we know the outcome in the training data set. When we don't have labeled data, we can pay to have it labeled using SageMaker Ground Truth, or we can say, well, let's just use an unsupervised algorithm. So the big difference between supervised and unsupervised is that with unsupervised projects or machine learning algorithms is they don't require us to have labeled data. We don't have to know the outcome in the data set. So many of these algorithms will do things like clustering or grouping data together, which you can see in the next example. So here we have the original data. If you ignore the image on the right, if I could block this off here, let me just do that real quick using somewhat rudimentary means, all right? So if you look at just the left, all right, the challenge here is the machine has to uncover and create the labels itself. If you look at this data and you say, what patterns are in the data? Some of you with really good vision might say, hey, there's a pattern down here where data is clustered together, but the rest of this, I don't see any relationship at all. And that's why you say, I'm going to use an algorithm, and a clustering algorithm will choose or show you that this data relates to all the data points near it. And it even uses colorization. So it changes it to blue or leaves it as blue. And then this gets changed to green. And this cluster, the real clustered area down here gets changed to red. Now, you may say, well, what's the big deal with that? Or what's the benefit? We're talking about things like healthcare and diseases. This can be very, very important. So it could be something where it's like cancerous or it's benign, or further testing might be cancerous might be red, benign would be blue, and green would be further testing required, or a different type of test should be taken for further analysis. So unsupervised learning basically does not require label data. We don't have to know the outcome of a particular data set in order to basically get some predictive outcome. In this case, just grouping the data in what we call clusters. And clustering is a very common type of algorithm that's used in unsupervised learning. Now we want to look a little bit closer. The next example for unsupervised learning is with speed cameras. And I always find this really kind of peculiar or funny, unless we were in Germany. If you look at the scale, it goes from 0 to 250 miles per hour. And if you live where I live, there's not a lot of cars I see driving around I would want to ever see going 250 miles per hour, unless it's some kind of AI thing on Reddit or something. So about the halfway point up this graph on the y-axis is about 125 miles an hour. All right, so our scale's a little bit off. I just want you to ignore that or chuckle about that, and maybe imagine 100 miles an hour or 125 miles an hour as sort of the top level. Just give me a little bit more about the use case for that, because fractional values could still be, or at least decimal values can be emitted from a regression problem. So here again, we've got basically a very big scale for, up to 250 miles an hour. So what they're basically showing you is that most of the data is fitting within the overall category here. So we've got a lot of the data sets or the data points all in this group, and then we have some false positives. The false positives are kind of okay. Yeah, Jacqueline, I might not hold up the class with that question. I'll just email it to myself and get that out to the group. Sorry, here we go. Sorry, I just got to paste all this stuff into my email so I don't forget it. All right. So again, we've got some numbers here where we're basically got most of the data points that are close to each other. All right. And then we've got some outliers. And in the class, we talk about outliers being both good and bad. So they can add richness to the data, and they can also skew our results. So they're kind of a mixed bag. But what they want to point out here, without getting into the confusion matrix and some other stuff that we talk about, like false positives versus false negatives, etc., and true positives here, what I would just want you to remember for this example, true positives means that we need to fix the speed cameras. All right. So, in the case of the red values or the true positives, those are indicators of hardware failure. And we actually would be the company. In this case, we're just kind of assuming we're the company that does or manages the speed cameras, or the government, depending on where you're at. And basically, if we see true positive values, that means people are going something like 230 miles an hour. Most cars, as you know, don't do that. Even the supercars kind of level out at around 200 miles an hour for the most part. So these are really, really high speeds, and that usually indicates that we need to get maintenance to go out and fix or replace the camera. Where some false positives, are just indicating that they're going faster than they actually are. If you are the person in the false positive category, you might have a ticket. So that might be important to you. Depends on the audience for that data. But most of the data is in this sort of normal realm, and we can sort of group that in this one sort of oval of data that makes sense, right? Except, may want to talk to people that are going 20 miles an hour on the interstate, things like that. But for the most part, we want to leave this data as is and focus in and say, okay, we've got some true positive. Let's go out and fix those speed cameras. There's obviously something wrong. So again, that's kind of supervised and unsupervised at the high level. The next section we want to talk about is reinforcement learning. With reinforcement learning, we're kind of changing gears a little bit. Most reinforcement learning applications are for robots, for self-driving vehicles, but reinforcement learning is now part of ChatGPT and some other use cases as well, where we basically want the model to be rewarded or penalized based on its behavior. But the example we have in the class and in this slide deck is Deep Racer. If you haven't seen AWS Deep Racer before, it's basically sort of a nerd fest, to be honest. Maybe pot calling the kettle black, but it's basically where grown-ups can go and race cars against each other using artificial intelligence. And there's all kinds of prizes, and it's at many of the AWS conferences as well. Basically, it's saying reinforcement learning, or RL, as you might see it abbreviated, is learning through trial and error. And please don't go out and buy the Deep Racer. You can just use a simulation of the Deep Racer and avoid paying $400 per car, unless you're a big company and you want to do this, in your own environments to kind of as a group activity. But notice how it says reinforcement learning is best when the desired outcome is known, but the exact path to achieving it is not known. So really what's happening inside of each of those cars is there's an agent running on each of the deep racer vehicles. And when we get through these data points, you can see here, we've got different data points on the track itself. And when this car successfully navigates this corner and doesn't run into other cars, it gets a reward. And when it basically smashes into another car or drives off the track, it gets a penalty. So to kind of demonstrate that, we have the agent running on the Deep Racer. Deep Racer's got a little camera on the front of it. It's a cool little vehicle, but it's basically learning from its environment. So if it does well, it gets a reward. If it does poorly, it gets a penalty. Again, a very different type of machine learning, but very important. I don't know if anyone saw, there was a self-driving car pulled over. I can't remember where it was. I think it was Austin, but I'm not positive. And the police pulled it over, and it did pull over. It stopped. So somebody thought about that use case and said, okay, if red and blue lights are seen in the back camera, pull over. But as the police got out to interview the driver, there was absolutely no driver. It wasn't one of those where they had a test driver for safety or a supervisor driver or whatever. The car is empty. So the police went to go talk to the person. There's no human being. The police don't really know what to do because that's kind of a corner case. And then the car just drove off, and they didn't chase it because it was like, who are we gonna put in handcuffs when there's no driver? So there's a lot to be learned, so to speak, in reinforcement learning. But basically, to summarize it, you've got this reward or penalty. Some people use the term carrot and stick. And one of my students basically said, think about reinforcement learning as any time where typically a device, but could be another type of model like ChatGPT, is learning from its environment and from its experiences, so to speak, and rewarded for good behavior, penalized for bad behavior. And some of it can be very, very serious, because if we're talking about self-driving vehicles, for example, or self-flying vehicles at some point, the risks are pretty high, especially if humans are involved. So that basically is it for the kind of three categories of machine learning. There are lots and lots of different algorithms that can be used and can be customized for use in each of these categories, but this is a kind of good idea to keep track of sort of the high level differences before we get into deep learning. And speaking of deep learning, basically what we're talking about here is a much more powerful solution, but it's a subset of machine learning. So you may have in the news here, they're always talking about AI, artificial intelligence is everywhere, but artificial intelligence is the overall category. And really the more powerful solution is machine learning. And then the even more powerful or the more complex problems can be solved with deep learning. So if you look at this graphic, excuse me, we've got the complexities of the problems that can be solved at the bottom. And the hardware-based constraints on the right-hand side. So really what we're talking about here is kind of borne out in a later slide, which we're going to talk about before we get into the machine learning pipeline. It'll make a lot more sense once we talk about that ImageNet competition coming up shortly. So machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. And of course, we abbreviate everything, so it's AI, ML, and DL, although deep learning is usually spelled out. But what we want to do is kind of keep this in mind. So what we talked about up to this point was machine learning and the three categories inside of machine learning. There are lots of different neural networks. And we talk about the artificial neural network, or ANN, but there are many, many types of artificial neural networks, or neural networks in general. So basically, we want to show you an example using chess. So keep these categories in mind: AI, ML, and deep learning. For AI, machines that can play chess based on rules. So pretty high level. An AI service typically is rule-based and can be somewhat limited on what types of problems it can solve. If we look at the machine, so that's the AI category. AI is machines that can play chess based on rules. Machine learning is where we use machines that learn to play chess from analyzing past chess games played by humans. So that is powerful, and depending on the humans, like if we were looking at some of the chess masters out of Russia or more recent younger chess masters coming out of the States and so forth, that's pretty powerful. But check out deep learning. Deep learning is showing you where machines can learn to play chess by playing against themselves. So we don't need any human data. We just need machine power. So what you're not seeing on this slide is, well, deep learning uses or typically benefits from the use of really powerful GPUs or graphics processing units, in addition to powerful CPUs. Whereas those aren't as important for machine learning and hardly at all important for AI. But deep learning requires a lot of grunt, a lot of power on the physical side, on the, I guess in cloud terms, on the virtual machine side of things. So what they mean by hardware-based constraints on implementation is saying the more we go towards the deep learning level, the more power we need, the more we're going to benefit from GPUs, and even more so from clusters of machines with GPUs. So I'm going to kind of explain that in a few slides. We just want to talk about what deep learning is first and compare it to the classic programming approach we talked about earlier and the machine learning approach we talked about earlier, and kind of show you how it's a little bit different. But to keep things kind of simple, they wanted to show you a neural network, in this case, an artificial neural network. And in this artificial neural network, what you need to see here is actually that each of these lines of neural or neurons is a layer. All right, so we have 1, 2, 3, 4, 5, 6 different layers. And the weights and biases and all the values and features, all the data can be updated as we go from one layer to the next. So we can take raw data and we can choose a deep learning algorithm and feed that data into that deep learning algorithm. And a lot of this work is done for us. So notice how it says the models can be trained on the raw data, but in addition, we can extract features automatically in the neural network. The process is iterative and uses multiple layers, but we don't necessarily have to update anything between those layers. So they had a cute little cat or dog picture in blankets. They switched it to this kind of average looking young person with sunglasses on, and it's a little bit out of focus, all right? So in this example, we are using the input pixels on this layer, and notice how we're passing data on to the next layer. We're looking at the edges in this layer, the corners and the contours in the next layer, the object parts, and then the object identity is our output. So hopefully, as a result of this neural network running on this particular image, it's going to say that she is a person. I guess arguably you could say humans are animals, so we might have some confusion here. Maybe put non-person in this category. And she's definitely not a car. So if it predicts that she's a car, we need to look at, you know, a lot of the configurations within our deep learning model. But this is a very, very simplified view of neural networks. So I'm just going to put a link in for those of you with a little bit more exposure to this. Get you some further reading there, and try and choose a site that doesn't give you too many pop-ups. Analytics Vidya is a very common, a very good source for information about deep learning. So I'm just going to put ANN versus CNN versus RNN, and yeah, just a little bit of further reading in the chat. So it is a very, very fascinating area of thought, but very, very involved as well. So just a little bit of extra reading there. But let me backtrack just a few slides. That's showing you sort of a more detailed version of this slide, where we have 2, 4, 6 layers. But remember, with deep learning, deep is sort of implying, you know, how deep we can go in terms of layers. So there could be dozens or hundreds or thousands of layers, depending on the use case that we're looking at in the algorithm, et cetera. But we want to kind of bring this all back to what we talked about earlier. And so we have our classical programming model. We have our machine learning model, or how we handle machine learning using models. And then in deep learning, you can see the artificial neural network is deriving the features as opposed to here we had manually engineered features or manually selected features. With artificial neural networks and other types of neural networks, we can derive the features from the data that we feed to it. And then we can pass new data into that artificial neural network and typically get better quality predictions than just a normal machine learning algorithm. But one thing that you might hear deep learning and it would sound like, especially those of you that are younger, it's like, this has been around for eons. And in theory, it's been around for decades and decades, but we couldn't really implement it due to the constraints we talked about earlier. So because of hardware-based constraints, we want to give you a little bit of a timeline with what happened with deep learning. And to give you that perspective, they look at something called the ImageNet Large Visual Scale Recognition Challenge, which also gets abbreviated to the ILSVRC, if you want to look that up. And it starts out in 2011, where people were submitting these single network algorithms to solve something where, if you look at the graphic, 94.9% of the time, or 94.9 was the level of accuracy for human predictions. So in 2010, 2011, it was probably pretty disheartening for the teams that were in this competition, because their accuracy numbers are around 71 to 74%. So there was an improvement between 2010 and 2011, but this is where you need to look at, what's going on. We don't have the physical power in our hardware to solve for these deep learning algorithms. So as time went on, you start to see that the accuracy in the single neural or single network deep learning algorithm starts to jump up. And I wish I was a little bit more time-lapsey here. In 2012, we had 81.8 accuracy. So that was actually the first year that an artificial neural network was used as a pattern to solve for that problem, to basically classify, I think it was a million different images down to, I think it was 1,000 classes. Basically, once we got to 2012, things started to change and you saw the uptick. And in 2015, our accuracy went up to 95.51. And then it's sort of like getting to the speed of light mathematically. It doesn't go up that much. So it goes from 95.51 up to 96.67. And it's going to slowly improve over time. But it's not going to, people looking for 100% accuracy need to be kind of warned away from machine learning. That's not typically something that we're going to achieve. But 90s, high 90s, definitely something that we can achieve with different algorithms when we're taking on these projects. So even though you hear deep learning a lot, and you might think it's been around for decades and decades, the first year it really started winning competitions and things like that, and in this particular case was 2015. So about 9 years since it beat human accuracy. And so that's really the kind of scope for deep learning. Even though it was theoretically something discussed for decades previously, we did not have the physical hardware to kind of pull it off. So again, think about the differences. This is a pretty good slide to keep in mind. And that being said, when you start to look at everything with the same lens, that analogy, like when you have a hammer, everything's a nail, bear in mind, there are use cases where it's still going to be classic programming. So, machine learning is great for predictions. Deep learning is even better at learning, especially when we don't have labeled data, for example. And we have data at scale and we want something really, really powerful. But classic programming could be a use case if it's just sort of a lookup to a database or something we can solve with code. So I want you to leave the webinar thinking, okay, sometimes it's classic programming, sometimes it's machine learning, and sometimes it's deep learning. Keep an open mind about what you want to use to solve a customer's problem. All right. That's going to take us up to the machine learning pipeline. So we're kind of on the downslope of this particular webinar. So I'm going to basically talk about the pipeline, and then we're going to show you a use case that's based on Amazon.com and their call center. And then I'm going to pass it back to Miles, and he's just going to talk through and maybe do a Q&A here about the classes that are available. What are your next steps? But I just want to spend a little bit of time talking about the pipeline itself. All right, because this might not look familiar to you. Some of you might be already implementing this, but this is a pipeline in terms of the process of solving for a machine learning problem. All right, this is not an automation talk, or don't confuse it with SageMaker Studio pipelines. That is an automation with directed acyclic graphs, et cetera, et cetera. This is really saying, how should you go about doing a project? And everything that you see in green can basically be solved within SageMaker. It's not really clear from the graphics, but everything you see in green are things that we can solve with SageMaker. And the things that you see on the bottom, we might be able to solve with SageMaker, but the things on the left, business problem and problem formulation, are usually problem solved using Microsoft Word or word processing, to keep it generic. So the business problem has to exist or there is no project. It's really important, but it's not something that we feed straight into SageMaker at this time and it just pops out a solution. We still need a human interface to kind of, okay, what's the business problem? Well, the customer has come to me and said, we're currently using classic programming to recommend hats and we're getting it all wrong. We're recommending, blouses to guys, and we're recommending work boots to women, and they're not necessarily construction working women. So that's becoming a challenge. A lot of our feedback is, what we're recommending doesn't really fit the customer's requirements. And so they're obviously not following recommendations. Now, what we need to do is something called problem formulation. All right. And problem formulation is taking that business problem and framing it as a machine learning problem. So saying, hey, well, what algorithms should we potentially use? We don't have to guarantee that we'll use these algorithms, but we want to suggest, we're going to try this recommendation engine algorithm and basically apply that using AWS SageMaker, for example, or Amazon SageMaker. And then we may, in that problem formulation phase, need to come up with a metric. So right now, they may say that the recommendations are about 50-50, all right? And that's not good. We want the recommendations to be 90-95% accurate. So we have to come up in problem formulation with an actual number. And a lot of customers I work with are consultants, and they say, well, what if the customer wants to choose? And it's like, you don't want to leave that open. You can't really start the project without knowing what your requirements are. So if they say, I want recommendations to be 100% accurate, you have to tell them this is machine learning, not magic. We're not going to get 100% accuracy, but we could get 95% accuracy or 90% accuracy, but we're not going to know that till we actually see some data, and we're not there yet. Remember, business problem and problem formulation is more a documentation exercise. It's a series of meetings, and best tip I can give you in a short webinar is make sure that there's one decision maker. The example of too many chiefs, not enough Indians, or too many cooks in the kitchen is spot on for machine learning. You want one person to say, this is the accuracy number. I agree with your problem formulation. Let's move ahead. If you have 5 different decision makers, it's going to cause major risk to your project. You want one, either the CEO or the CIO, CTO, et cetera. Somebody is going to make the call to document the measures or the accuracy figures that are required for the project to be considered successful in the problem formulation phase. So believe it or not, you might be saying, hey, Chris, you're basically, I think the English term is blagging. You're blowing smoke. I'm trying to think of politically correct ways to say that you're not really being accurate just yet. You have to tell the customer in the problem formulation phase, these are just estimations. We're going to know more once we get data. All right. So you kind of want to put some caveats in the documentation under problem formulation. But the simple, or to go back to, what is going on, is the business problem is what has to occur or be present for a project to proceed. And the problem formulation, it has to frame the problem as a machine learning problem. If you can solve it with classic programming, go for it. But you're not going to need the rest of this pipeline if that's the case. Now, data collection and integration is getting the data. And questions you need to ask are, do we have access to the data? Do we have permissions to the data? Any of you that come from a data science background know sort of the pitfalls of dealing with data and data silos and people that are, gatekeeping on data and not giving you permissions and all that. We need to make sure that typically in machine learning, we get a domain expert who can give us information about the data before we start collecting it. And those of you that are more AWS intense users, a lot of times the collection and integration are using services like S3 to actually store the data to be ingested into SageMaker. Data collection and integration is all about extraction, transformation, and loading and getting things right. But you kind of want to jump ahead to data preprocessing and visualization just to make sure you understand the data fully before you set up any kind of pipelines in the actual physical sense. So data collection and integration is, where's the data? Do I have access to it? Do I have permissions? How am I going to get it into my platform? And the lazy instructor or the hurried instructor in the webinar would say S3 is a very common location, but obviously there are different storage options in AWS depending on how fast you need to process that data. Data preprocessing, if I had the sort of horror movie sound effects on tap, I would be playing them here. You can lose a lot of time in preprocessing visualization. In some cases, 60 to 80% of our human time in machine learning projects gets tied up, and some people say wasted during preprocessing visualization. But this is where the rubber meets the road. This is where you actually can see the data. And this is where you can use different machine learning libraries to basically solve for this. So we don't really have time to go into all of them, but I just wanted to share them with you. So when you do have some time, you might go, oh, I'm familiar with those, or maybe you're not. These are all sort of publicly documented, for the most part, open source solutions. So let me just share those site links with you. Bear with me one second. There we go. So these are kind of well, for those of you who are going to move on to certification, these are the types of things they're going to test you on for the ML specialty certification. And so libraries, you should check out. I'll put that as sort of the overall category. And obviously ML needs to be there as well. So ML libraries you should check out if you're not already using them. These are very, very helpful. And they work very well within AWS platforms like SageMaker as well. But again, the kind of trend that I wanted to highlight here is that a lot of folks are already using pre-trained models. So a lot of times we can reduce the time that we have on data collection and pre-processing and visualization if somebody's already come before us and done the pre-trained the model. If they have not pre-trained the model, then we need to go through model training and tuning. And this is where SageMaker is really, really useful because it will do the training. We can basically choose built-in algorithms. We can bring our own algorithms or use marketplace algorithms. This is a very, very powerful tool within SageMaker that's sort of set up already for us. We just have to pick the algorithm and configure some values as far as tuning goes. And then after model training, we evaluate the model. So that's where we actually put a score that comes from this problem formulation phase and say, did we get to 80% accuracy, 90% accuracy, a high number of accuracy? If not, we might have to go back. So this business goal is set forth during problem formulation, like it's going to recommend the correct hat or the correct item to the customer 90% of the time. If that happens, we go to deployment, all right? Basically say we're going to, there's a couple different deployments. We can do batch or we can do real time. Either way, however we want predictions to be on a schedule or in real time, that's when we go to deployment. If we do not meet the business goal, then we need to look at maybe doing some more feature engineering, or worst case, we didn't have enough training data. So we need to go back and get more data and do data augmentation. So we're going to take an Amazon.com use case and apply it to this particular pipeline and show you at which stage we're at as we go through. But the thing I want to warn you about, so those of you that are new to machine learning, once you deploy, you are not finished. This should be sort of a flashing red light here of what if we get new data that is not in the same format as the existing data? Or the model just starts dropping in terms of accuracy over time, which happens. There's data drift, there's concept drift, there's all different types of categories of things going wrong once we're deployed. So please don't get in the habit of just deploying and walking away and saying, oh, there's my final invoice for the company or whatever for my work, or my team's work, you either want to train the customer how to monitor models ongoing, or you want to have some budget in your consulting contract that says we'll monitor the model over time and retrain the model as needed. So just because you're deployed, unlike a software application that may be fine for 6 months or 12 months, you want to monitor it in case the accuracy drops or something happens, the data changes, things like that. That could cause your accuracy numbers to fall below what the original business goal was. All right, so probably the most important slide in the deck is this one. So kind of a mental picture of this is a good idea. This is the process of how machine learning works, not the automation part of it. That's an additional functionality that we can use in SageMaker Studio. But this is sort of the ground level project plan for any machine learning project in the eyes of AWS, at least. There might be a few variations if you look at a generic model, but this is basically how AWS looks at machine learning problems and solves for them. Now, we want to give you one use case. There's lots of different use cases, but basically this is a predictive routing use case. And this is a problem that a lot of companies have and a lot of us have faced. So you make a phone call, you get in, and maybe you hit 1 or 2 or 5 or whatever the prompts were that you got. And you end up in the wrong department. The wrong department says, oh, I'm sorry, you're in the wrong department. You need to go to tier 0 in this case. And then you find out tier 0 is not technical enough. And then you finally get routed to the correct agent from the tier 0 folks. So your time is valuable. A lot of people can sort of drop off the calls, lose a lot of customers or upset a lot of customers when this happens. So we want to apply the pipeline I just showed you to the Amazon.com call center problem. So the business problem is, how do we route customers to the correct agent as many times as possible, as much as possible. The machine learning problem is we want to look at patterns in customer data so we can basically get predict the accurate customer routing for that use case. So the business problem is, how do we route the customers correctly as many times as possible? And the machine learning problem basically says, well, how are we going to identify patterns so that we can basically predict the correct routing for future calls? So that's business problem and problem formulation sort of at a high level. And then data collection and integration, we're going to look at Amazon.com, as you probably all know, has a lot of data and they're really good at handling data. So we've got historical call records and agent skill sets. And some possible features might be, what were the customer's recent orders? Did the customers own a Kindle? And are they Prime members? So those can be suggested features. So that's sort of the things we want to start thinking about. Where is the data? Do I have access to it? Do I have permission to it? How am I going to basically get that data to my platform like SageMaker into my models inside of that platform? So in pre-processing visualization, you might want to look at things like agent skill sets, at least in Amazon terms. So do we know Kindle troubleshooting? Do they know Kindle payments, refunds, orders? And they use one of the worst visualizations, a pie chart. And if you look at the math inside the notes, they basically make some mistakes mathematically here. But returns is a majority of the data. Prime memberships apply to about a little more than a quarter of the customers. Kindle calls are kind of a smaller percentage, and the miscellaneous is a even smaller percentage. But if you look at the math in the notes, I know you can't see the notes. It says 40% are returns, 30% Prime membership, and 30% Kindle. We forgot to do the math on the actual miscellaneous. Yeah, goofy things can happen, but there are better visualizations. If you look at the links, using Matplotlib and Seaborn will give you an indication that we can use things like histograms and bar charts, correlation matrices, etc. But we get into that in more detail in the class, or in each of the classes for that matter. So another thing that we want to look at is briefly feature engineering. So it's not really a phase. If you look back at the pipeline stage, they don't call it out specifically. But feature engineering is basically improving the features so that the predictive outcome of our models is improved. So in this case, we have the most recent order, which is a hat. And then we have the date and time for the most recent order. And then we see that the customer either owns or doesn't own a Kindle. So what we don't really tell you here is that this particular value is harder for our algorithm to calculate. And we want to actually engineer a feature to change that value or to calculate that value to basically days since the last order. So instead of passing a complex date timestamp, we're just passing the value of 72, which equals the number of days since the last order. All right, so feature engineering might be taking categorical data and making it numerical, like we could take the owns the Kindle and make that a 1 or a 0 instead of a yes or a no. But really, for our algorithm, the most complicated thing is reading that date timestamp, converting that, et cetera, when we really just, it would be better for the algorithm to know how many days it's been since the last actual order or purchase. And then the training and tuning, they actually talk about a sort of complex concept. Some of you with machine learning backgrounds might say, well, we just do training and test data. In Amazon, we typically break the data that we have for training into 3 parts. So unless it's a really huge data set, there is a 70-15-15 sort of use case for really huge data sets, but most of the time it's 80% training data, 10% validation data, and 10% test data. So without getting too far down in the weeds, the training data set is split up because we don't want to have something called overfitting. And we also don't want to have something called underfitting. So it's best to split the data up in 3 parts. So we do an analysis on the training data set, and then we hold out the validation data set to test whether we get the same numbers. If there's a huge variance in accuracy, that usually tells us that it's overfitting. If we're just getting bad accuracy from the beginning, that usually typically means that we're underfitting. So we want to avoid both of those. And that's why we typically have this model where we split the data in 3 parts. And then the test data set, we actually hold off until the very end to see if it meets the business goal. If we go back to our graphic with the pipeline, we hold the test data set out till the very end. Basically, model evaluation will let us look at the test data. And if we don't meet the business goals, we need to look at feature engineering and data augmentation. If we do meet the business goals with test data, then we're ready to deploy. And then remember, don't just leave the deployment as it is. You want to monitor that ongoing. So that's model training and tuning, but it kind of bleeds over into model evaluation. So basically, after running a training job, we look at the test data set, see how things can be tweaked or improved. And we either deploy or go back sort of to the drawing board. But model training is where training and tuning is where we're actually going to, again, this differs a little bit from our actual, they are separate points. So look, I would keep an eye on this graphic as opposed to the steps. They're trying to make it fit within the topics that we're talking about for the Amazon.com problem, but it kind of skews the pipeline. So there's no real feature engineering step unless you look at these slides that are talking about the use case. So if we kind of explain what we're finding out in model evaluation, it's like, how often did we route calls correctly on the first attempt? How many times on average did the calls have to be rerouted? And do these results meet our business needs? Or some of the key things for model evaluation. But at the end of the day, we're hoping that from our original graphic, we're not messing around with any of the other departments. We get the customer to the correct agent as many times as possible. Maybe not 100% of the time, but definitely improved from where we started, where it was getting 1, 2, 3 different misrouted calls, and we weren't getting to the correct agent. So I know that's a lot of info. If you have a lot of questions, things like that, just on SageMaker in general, remember my email's in the chat. And there are a lot of resources available to you on AWS. Machine learning page is a good place to start. But I think at this point, might want to get Miles back involved, just talk a little bit about some of the next steps that are available. And if there are any questions for me on machine learning, I know I owe all of you an email on Jackie's question of fractional use, but other than that, that's kind of it for the presentation portion.
And Chris, I've collected all the links that you put in, along with your email, my email, And I'm putting them all into a document. Hopefully we can get that sent to everybody when they send out the recording. But I'll put it into the chat as a document that you can download as well. Let me see if I can save it as a PDF maybe. I think that's probably the easiest way. Yeah, so I'm going to put this document in. Let me show it to you first. And I'll pop it into the chat. So depending on how your company has Zoom set up, you may or may not be able to download a file from the chat. But I put it up there. We'll see if you can see it in the chat. You should be able to download it. Let me just share my screen. So this is the document. So it's a few different links that Chris put in. Oh, I included this other link that you had before on overfitting versus underfitting because you mentioned it. We're going to talk a little bit about these upcoming AWS machine learning classes. So we have a number of classes. The main class, if you've not done much machine learning, is this 4-day class called the Machine Learning Pipeline on AWS. And that's the one that, after you take that, if it all goes well, you should be in a better position to go for the AWS Machine Learning Specialty Certification. So that's the course that most closely aligns to that cert. And it's a class that we run fairly often. So we have one coming up August 22nd, September 5th, September 22nd, 26th, so on. The other class that's kind of a deep dive on SageMaker specifically is the SageMaker Studio class. Now that one, Chris, you teach both. That one you said is if people already know some machine learning basics, maybe from somewhere else, and now they need to learn, understand AWS's tool set specifically, right?
Yes, I would say SageMaker Studio for data science is an advanced class, and you should definitely know machine learning before you take that class. It's very hands-on. So the 4-day class is best if you're brand new to machine learning. That's a good place to start.
Yeah,
and then SageMaker. Sorry, go ahead, Miles.
And then the ML Ops engineering would be a follow-on to either of those. When you want to sort of productize your ML and churn it out, kind of borrowing the DevOps concepts, right? Is that sort of what's covered in that class?
Yeah, it's DevOps for machine learning. So
okay,
if you know DevOps, you kind of head start on that.
Yeah, it's expecting people to know the DevOps tools in AWS. So there's a pretty heavy duty, like maybe taking the DevOps engineering class from AWS first, I think would probably get you there. And then the 1-day deep learning class, you wouldn't take that just on its own, right? We actually don't schedule it publicly. If you've got a group of people and you want to deep dive into that very specific element of, building neural networks and all that, we can still offer that class, but it's not something, if we just put it on our public schedule, somebody looks and says, oh, 1-day class, I'll take that instead of the 4-day, and then they're in over their head immediately, right? So that's the idea. AWS does have something called the ramp up guide. So that's a document that you can use to help, find, both the free resources that AWS has through Skill Builder. They also suggest these classes that we run. And if you are interested in any of those classes, we have a summer promo on right now. Let me just pull up that. Let's see if I can find everything I'm looking for here. Yeah. So here's the promo. It's basically $100 per day. So the machine learning pipeline's a 4-day class. When you sign up, if you sign up before August 31st and you put in the promo code upskill 500, you'll get $100 a day off. So $400 off the price. So that's pretty good. I think you have to take the course by November 30th. So this is sort of, this is going to end August 31st. We might end up pushing it to September. So just, come back to this website. That link is in the thing that I put in the chat. So what else did I want to say? Oh, so that's the summer promo. On our resources section of ExitCertified.com, we have a lot of webinars, so including all these discovery days. So the past discovery days, we did one on security, one on migration. I did this one just on fundamentals of modern data strategy. So these ones are all recorded and on there now. But we have some other ones, maybe you're in Azure world, you're preparing for the Azure admin certification, the AZ 104. I did this one earlier this year, was a public cloud comparison, talking about the big four public clouds. So, we've got a lot of webinars there that are available. The Ramp Up Guide is a great resource. Oh, yeah. Yeah, so that's a couple of things I wanted to mention. And, AWS, we've got a lot of AWS courses, not just machine learning. And in fact, wanted to kind of point out, we've built these learning path documents. They're sort of mostly focused around the AWS certifications, the popular certifications. And so the machine learning one here, it's called the machine learning specialty. We would suggest, obviously, that 4-day machine learning pipeline class is the one to prepare you for it. You probably need just a very little bit of AWS knowledge. So maybe just the 1-day tech essentials, so that you can navigate around AWS. You understand the permissions and the idea of users and groups and doling out permissions, and some of the things you need to be able to use basically any AWS service. And so that's 1-day tech essentials is normally the one day that we have at the beginning of all the paths. If you've already been using AWS for a while, skip it, right? And so our most common path is probably the cloud architecture one, where you come in, maybe you do the tech essentials, and then the 3-day architecting class, and the solutions architect associate is by far the most popular certification that we have. So maybe this document I can throw in the chat as well, if you're interested. Pop that in. I did share the PDF file with you, I think. Was anybody able to get? Let's see if we can.
I think Sumi's talking about what you just shared. You're good to go.
Okay. Oh, he's looking for that one. Yeah. Okay. I just threw it in. Last thing I wanted to mention is just ExitCertified does a lot more than just AWS training. We're partnered with all the major cloud vendors, and also a lot of IBM and Oracle and those kinds of companies, VMware. But we use this diagram. We call it Cloud-Centrics diagram. Kind of hits home. At its root, we're partnered with the major public cloud vendors. We offer their authorized training. But then you get into areas where, hey, I just need to learn about Python and data science, and some of those things for on the analytics side, or maybe you're more on the infrastructure side. You need to learn about Docker and Kubernetes and just microservices architectures in general. So we have a lot of classes that, even if there's no vendor of note, they're just sort of, we go out and find out who's got the best class on Kubernetes. And so we have a few options there. So we call it Cloud-Centrics. This is just a diagram that kind of hits home. And when you get to the diagram, like if you look at analytics, you click on that section, it takes you to that part of our website. And then you can, delve deeper in. We've got, logos there for the different cloud vendors, or, maybe you need to learn Spark or something like that. We got a few different ways to learn Spark. We've got classes from Databricks on Spark. We got classes from Cloudera. We have just some regular PySpark classes. So, there's a lot there. And so I put that into the, I put that link to the Cloud-Centrics. Oh, there, right there. I knew I had it somewhere. So that, and the last link I put in was one that I went to the AWS Summit in New York this past week. We had a booth. And one of the keynotes, they were talking a lot about generative AI, and AI is very broad, right? And Chris today was really talking specifically about machine learning. But with ChatGPT and now AWS has Code Whisperer, and we see all these generative AI services popping up. You may be interested in using these tools where I don't have to be a machine learning expert at all, right? It's putting a tool in every developer's tool belt. And so they announced a few new generative AI, services. And so this sort of gives you a nice rundown about what they talked about. Um, Something called Amazon Bedrock. They actually added to it. They added a whole bunch of stuff to it. Some of the other ones, vector support for open search serverless, so on, so on. I don't want to get too much into it, but if you're interested in, what's new in AWS on that side of things, I thought I'd throw it in. If generative AI is your thing, we have a webinar. We haven't announced it yet. One of our colleagues, Ken Kruger, has built a really nice, specifically for developers. He kind of compares all the different tools out there. If you're a developer and you want AI to kind of generate the code for you, there's a lot of options now, and he kind of is going to do a survey of those. So keep your eye open. However you found out about this webinar, watch for our upcoming webinars. And we have AWS in all the developer classes has added more information on Code Whisperer, but on the Microsoft side, they have some open AI classes coming. There's a one-day generative AI class. We have some other non-vendor materials just talking about prompt engineering and some of those ideas as well. They're not something that run on a public schedule. If you have a group of people that need to do it, we can do group training. Most of our classes, if you go to that AWS schedule, if you look at any particular class, like say the ML pipeline class, wherever that went, here it is. When I click on that one and I go down to view schedule, you'll see, August 22nd, it's in McLean, Virginia. I think if I click on virtual, you'll see all the dates really quickly. And you'll just see one of each date. The virtual ones tend to run, the ones in a particular training center, we rarely get enough people to send an instructor to one of our training centers. But the virtual part will generally run if we get a few people in it. And there are definitely some of the classes where we guarantee them to run. I think the next SageMaker Studio is guaranteed to run. Let's go look. So on our website, let's just look at the virtual dates. Yeah, the one September 13th is already, if you see that GTR, that means it's guaranteed to run. So that's probably you, Chris, teaching that, I would imagine. They probably got you penciled in for that already.
Yeah.
So that's kind of what we've got out there. If you have any questions, you can send them either to Chris or myself. If it's a question about ML, I think send that to Chris. If it's a question about ExitCertified or classes, anything like that, send it to me. Like I said, I'm going to try and get this document sent in the email that goes out to everybody. But for now, hopefully you can grab it from the chat. All right, so I'm going to stop sharing. And we'll stick around for a couple minutes in case there are any questions. But otherwise, I don't know, Chris, that was pretty much, I think they book us for 2 hours and then they, it's really an hour and a half material, right?
We're good to go.
Yeah.
Thanks, Miles.
All right. Oh, one thing I wanted to mention, as you leave the session, there will be a little short survey that pops up, just a couple questions asking you, what'd you think of this? What other topics are you interested in? We're just trying to keep our finger on the pulse of customers and figure out what are they interested in. So if you can fill out that survey, I think you have to end, if we end it, it just throws everybody out. But if you guys leave individually, it'll pop up that survey. So we're going to stick around and hopefully you can fill out that survey on your way out. Probably should have mentioned that before people started leaving. And Chris, thanks a lot for taking the time to do this for us today.
My pleasure. Thanks back.
I'm going to hit stop on the recording.